The second thing that I want to cover is Dalton's law of partial pressure. And looking at this drawing, you have 1, 2, 3, 4, 5, 6 particles, yeah? And in this diagram right here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I have 15 particles that is creating a certain amount of pressure inside. Versus over here, I have a certain amount of pressure caused by the 6 particles inside. Dalton's law of partial pressure says in a mixture of gas, the total pressure is a sum of the partial pressure. So the total pressure is going to equal the pressure of caused by one of the gas plus the pressure of caused by the other gases. So if I were to mix these gases together, I would have a mixture just like this. And if I know that the pressure inside this canister is 2.9 atm, and the pressure inside this container is 7.2, the total pressure of the mixture of these two gases is going to be just 2.9 plus 7.2, which equals 10.1 atm. So now let's apply this theory or this law to an example. This is air. Air is mostly made up of nitrogen and oxygen. So if I were to add up the pressure in kPa of all the various gases in the air, you would get 101.3 kPa. Second example is this right here. Let's say that I'm doing a lab, and I am collecting some gas. So let's actually do acetic acid with baking soda, and I am making CO2 gas. So here is my CO2 gas, and I am collecting this water or this CO2. This is going to produce water, this is going to produce CO2, and the CO2 gas is going to come up here and through this water, and I can capture the CO2 by let's say that I am doing an experiment and I am mixing acetic acid with baking soda, and I am producing CO2 gas, and this bottle was filled with water, but the CO2 gas is coming in through this hose and coming into this bottle. This allows me to collect the CO2 gas while displacing some water. Okay? So in this container now, I have CO2 gas, but I also have another kind of gas, and that other kind of gas is the water vapor from the water that was in the container. And please remember that the water vapor is dependent on the temperature, and I'm telling you that the temperature of the room is 25 degrees Celsius. From our podcast 2, we know that there is a table that we can refer to, and the table is provided right here. And at 25 degrees Celsius, the pressure of water is 3.2 kPa. So I have water vapor at 25 degrees Celsius is 3.2 kPa. And I know that the air outside, so actually this is during the lab, this is after the lab, this is a CO2 with water. And remember that that we're assuming that the the experiment is done at sea level, and so the pressure of outside is standard pressure at 101.3 kPa. If the water level inside the container and outside the container are the same, then the pressure inside the container as well as the pressure outside the container must be the same. If the water level is the same, then the pressure inside and outside the container is the same. So I know that inside the container, the pressure of CO2 plus the pressure of H2O is 101.3 kPa. I know that the pressure of water vapor is 3.2 kPa, so pressure of CO2 must be 101.3 kPa minus 3.2 kPa, which comes out to be 98.1 kPa. And so that is the partial pressure of CO2 and the partial pressure of H2O was 3.2 kPa. So this is a second example of Dalton's law. It says consider the diagram shown above actually. Okay. So in this diagram here I have hydrogen gas and the pressure inside is 63 millimeters of Hg and the total volume on the left hand side is 1 liter. The oxygen gas is trapped in the smaller container, which is only 0.5 liter, and the pressure inside here is 403 millimeters of Hg. I want to know the partial pressure of each gas when the stopcock is open. So I know that before I open the stopcock, let's talk about oxygen only, and I want to know, I know that the initial pressure was 403 millimeters of Hg. I know the initial volume was 0.5 liters. And I don't know the partial pressure of oxygen after I open the stopcock, but I know that the total volume is going to be 1.5 liter. So here is my P1 and V1 over N1, T1 equals P2, V2 over N2, T2, and I'm not dealing with number of moles, I'm not changing the number of moles, nor am I changing the temperature, and so here is my Boyle's law. So if I were to plug in my numbers, 403 millimeters of Hg times by 0.50 liter is equal to P2 times by 1.50 liter, sorry, this is 1.50 liter, then I would get P2 of 130 millimeters of Hg because of sig figs. So now I know that the partial pressure of oxygen is 130 millimeters of Hg. So I'm actually gonna erase some of this. So okay. I'm gonna give myself some room to write. So now let's start doing partial pressure of H2. I know once again that previously, before opening the stopcock, the pressure inside was 63 millimeters of Hg, and my volume was 1.00 liter. My P2 is what I'm looking for pressure inside after I open the stopcock, and the total volume afterwards is 1.50 liter. So once again, P1 V1 equals P2 V2. I have 63 millimeters of Hg times by 1.00 liter is equal to P2 times by 1.50 liter, and my P2, which is the same thing as my partial pressure of H2, comes out to be 42 millimeters of Hg. And so my total, what would be the pressure in the flask or in the in this apparatus, when the stopcock is open, the total pressure will be the pressure of H2 plus pressure of O2, which comes out to be 42 millimeters of Hg plus 130 millimeters of Hg, and that comes out to be 172 millimeters of Hg. Yeah. Or more like 170 millimeters of Hg, because I really don't know this number. Okay? Okay. Now, going forward, Graham's law. Graham's law, in order to understand Graham's law, I need to define some vocabulary, and I want to define effusion and diffusion. So diffusion, as you guys all may know, it's a tendency of the molecules to move towards areas of lower concentration. So if I were to remove this partition right here, the gas particles will flow into the other side because there are less particles here on this side after I remove the partition. Effusion was only created because diffusion had so many variables that they needed to limit the number of variables involved to measuring the rate of diffusion, or measuring the rate of effusion. So this is just for simplicity's sake. Effusion is a process of molecules escaping through a pinhole. And so, oftentimes people equate these two words as the same, but effusion is more specifically defined as the process of molecules escaping through a pinhole, and it was only created just to simplify calculations. Graham's law says the gases of lower molar mass diffuses and effuses faster than gases of higher molar mass. So, gas particles that are heavy move slower. The rate of effusion of gas is inversely proportional to the square root of the gas's molar mass. This law also applies to diffusion of gases. What the heck does that mean? In order for me to explain what that means, I'm actually going to switch over to my to another setting. Hold on a second. On this setting, I'm unable to write for you, but please listen to me carefully. The red particles that you're about to see move are the helium particles, which are really, really, really light, versus the blue particles are represented as krypton, and these krypton atoms are pretty heavy. So I'm not talking about necessarily the size of the particles, but the larger blue dot is supposed to represent the heavier atom, and the red dots, the small red dots, are supposed to represent the helium atom, which is a lighter atom. So I'm going to start the simulation. By looking at the simulation, you can see that the red dots are moving much faster than the blue dots. The red dots that are lighter are moving faster, and the blue dots are moving slower. But this is at one temperature, meaning that the average kinetic energy of the blue dot is equal to the average kinetic energy of the red dot. So let me explain that a little bit further, and I'm going to switch settings once again.